So, hi everyone, and welcome to another of our webinars from the HKPU Xinyan chapter. Today we are transitioning to a different format to what we are normally used to. So we are going to be holding a mixed webinar here today. Today we have Dr. Xinyan Huang. He's an assistant professor at the Hong Kong Polytechnic University. He received his PhD at Imperial College London, and before moving to Hong Kong, he stayed at UC Berkeley, where he undertook a postdoc in research with spacecraft fire safety. He has called for more than 100 journal papers, and he has received several awards, as you can tell in the screen, including awards from the Combustion Institute, the IFSS, the Institute of Physics, and of course, also SFP, the 5 under 35 authors. So thank you for joining us and thank you for your time. We are really honored to have you here, and the floor is yours.
Thank you for the introduction. Yes, it's really an honor to be here. And it's actually my first international travel post-COVID, so it's very nice to do face-to-face class rather than just stay online. And I see a few people still in the video. Adam, please fix that.
Yeah, we'll fix that.
Okay, so I will do today's talk is about smart firefighting driven by the artificial intelligence. So this is a work we start to do since 2020. So it's like 2.5 years of work. And this is a project funded by the Hong Kong government. It's called Surefire. And Professor Asif Yusmani is the project coordinator. So it's actually a big project, involve lots of university and research institutions. So, and I just want to share some the progress of this project we have done over the last 2.5 years. Okay, so I will basically divide the talk into 5 parts. First, I will give very short introduction about the AI, artificial intelligence, and the fire safety design. Then I'll talk about the fire recognition by AI, the building fire digital twin, smart fire focused and firefighting, and some challenges and perspective. I just give some of my own ideas, and it's free to discuss. So let's start with the introduction of AI. So we all know it's a hot topic, but it's not something new. It has been proposed, let's say, half century ago. So I think the first one is Alan Turing, who proposed the imitation game. So basically, if the computer cannot tell whether the guy talk to you is a computer or human being, then it's artificial intelligence. And later on, we have this famous Dr. Ma's workshop. A group of young people propose very important concept of artificial intelligence and machine learning. And of course, most of these guys are the leaders in this area, but at that time, they are still very young. So this is not really a new concept, but the development of the AI is not so smooth. So if you look at this time evolution of AI, we know there are like a few peaks and tops. So there are like 3 AI booming. We are actually now in the 3rd booming, but after each booming, there are some winters. So we have 2 winters already. Something we don't know is whether it will keep booming or there's a 3rd winter after recent booming. So I just briefly talk about why there are AI winters. So the first winter happens in the 1970s. Everyone is happy about the concept of AI. And so initially people want to, for example, translate using AI to translate different language. And what they do is they teach the computer the grammars, just like what we study English. So initially we teach how to use the grammars, but it turns out it's impossible. So for example, the translation between Chinese and English require more than 100,000 different rules and still cannot translate very well. So it doesn't work. So it enters winter in 1970s. And later on, people realized, okay, we should not use this kind of expert system. We actually use statistic approach. So we actually need to train the computer with some translation, for example, between English and Chinese, and let them learn freely. They can grab the rules behind these translation. So they have the right approach, but the hardware is not there. At that time, in the 1980s, 90s, computer is very weak. The memory is very small. So you don't have the hardware to train such amount of data. Actually, there's not so much data at that time either. So it enters the second winter. And now we are booming. We are in the third AI booming. Why? Because we have big data. We have supercomputers now. And where are these data come from? So we generate all the data every day from the cell phones, from the internet, from social medias. Actually, we have so much of data. Even for the building, we have so much sensors. We have CCTV cameras. Actually, the data is already there. And the computer is also pretty good. And we have cloud computer. Even you don't need to have a physical computer in your room, so you can run super computing. So this is the reason we have the AI booming. So the question is, how can we use this kind of AI technology to do something to help the fire safety engineering? So if we look at a conventional approach, so what do fire engineers usually do nowadays? They do the performance-based designs. They run the CFD code to simulate the fire, and then use the result to give some design guidance, estimate the cost. So the idea of CFD is to solve physical-based equations. So basically now it's Stokes equation, energy conservation, mass conservation, like this. So this is a typical way we do it. But what humans do when they evaluate a design? So if you come up with some kind of fire system design and you show to a very experienced fire engineer or the regulator, if these people, they have read like hundreds of thousands different kind of design, they can just tell you without thinking whether your design is reasonable or not. And if you ask these guys, why do you think my design doesn't work? They cannot tell. It's just too much of information mapped in his brain, and he can tell something doesn't make sense. So this is actually human make decisions. So what we do is actually we have to combine the computer and the human beings to make it the artificial intelligence work. So what we do is we mimic the humans' decision making. So if we let the AI to learn different kind of design, like CFD simulations, we feed hundreds, thousands of different cases to AI, let it learn. So it will learn by itself. And eventually he come up with some patterns and can tell you whether this kind of flows, this kind of smoke propagation is reasonable or not. So this is the idea. We try to use AI to do the design. So something we start to do first is the HN file. That's probably the most widely used performance-based design case. So you usually have a large open space and you need to design the ventilation system, make sure that A set is larger than the R set. So that's a typical performance-based design. So what we do is we actually run like thousands of different simulations under different geometry, different shape, different volume, height, ventilation capacity, file size. So we run them and let the computer to learn, let the AI to learn the patterns. So whether it can give reasonable result or not. So I'll give you some demonstration. So this is a case, very simple one. So we have a large like square of the larger open space. And the left-hand side, FDS simulation, right-hand side, AI simulation. So basically, AI can capture most of the details, of course. Some of the eddies it cannot capture. And this is very similar. We also try actually with a different roof shape. As you can see that even you change the shape of the roof, the AI still can capture these simulation very well. So after you train with so many cases, actually AI can recognize this pattern. So we just use this principle to develop a tool. We call it IFE tool. So we have that software, open access online, in case you are interested. So I do a demonstration. Let's say if we have a large open space of 15 meters by 50, and if the height is 15 meters tall, let's say the fire size is 5 megawatt. Let's say the fire location is in the center, the soot yield is 0.1. Okay. And the extraction of the ventilation system, let's say 10 meter cube per second. Yes. Okay. So yeah, so this is I'm sharing this. So this is an open access software, and we want to keep the clearance height at 2 meters. So this is our, let's say, rough estimation. Then we just click once. So this is the result you get. And okay, let's say it doesn't work. Let's increase the ventilation to 30. Yep. So you get the result pretty simple, quick. If you change to 3 megawatt. So this is a smoke pattern you can see. So without running simulations, you get as accurate two-dimensional smoke motion, smoke visibility. You can also change to CO concentration, all these kind of things. Just let's say one click, you get a result. So we hope this kind of AI tool can help facilitate the fire engineering design without additional back and forth between designers and government agency. So the last thing I want to mention is the comparison between CFD and AI. So honestly, I'm not an AI expert, and my students are not AI experts, they are fire engineers. But it doesn't matter whether your background is, you can still use AI because AI is just a tool. For example, we all use CFD, but I don't think you guys can program CFD from the scratch. Basically, you use CFD as a tool. And the people who are using CFD are actually fire engineers, not the guys who program the CFD to do the fire simulation. Same here. I imagine in future, it will be fire engineers using very mature AI tools to help design the fire protection system for the building. So this is some concept I'm imagining for the future. Eventually, as I told my students, if you feel, some of my students working in the consulting company, if you feel your work is kind of repeating of a routine, which means it's very likely it will be replaced by AI very soon. So has to be very careful about that. Okay, that's the first part. So the second part I like to talk about is the fire recognition by AI. This is not something new either. We all use a smartphone, and they have the facial ID, which you can just use it to unlock it. So it's very widely used technology nowadays. So our question is, can we train the AI to recognize a fire as well? So just like using the phone to recognize a human face. So to do that, you actually need a lot of data, images to train the AI algorithm. So let me give you some example. So the first thing we're trying to conquer is we want to know if we can train the image of smoke to know the fire inside the building. Because once there is a fire, probably there's nothing you can observe the fire inside the building. Even you have CCTV camera, probably it's broken. So what we can see is just a smoke outside the building. But usually, if you have large smoke outside the building, which means you have large fire inside the building. So can we just look at that smoke image to get the fire inside? So this is our idea. So we want to train the fire image, a smoke image, and correlate it with the heat release rate of the fire. So that's the first step we do. So we use a numerical smoke image first as a demonstration. So we run the CFD simulation and use the smoke image, both the side view and the front view to train it. So let me show you a demonstration. So, the training we get is the smoke image outside the building, and the output we get is the heat release rate inside the building. And the dashed line is true value, the red line is AI prediction. So once you train the system very well, the AI can recognize the connection between the heat release rate and the smoke image outside it. So it can tell how big the fire is inside. So of course, this is a numerical image, but ideally it can be extended to real image. Okay, so the next step is we want to try something with real fire. See whether we can use a fire image to connect it with heat release rate. But that's quite challenging because you need a database. You need a very good database to provide these base data for you. And luckily, we found NIST actually did a very excellent job by building this fire calorimetry database. So they burn everything. They burn like chair, then burn the sofa, wood crates, and they build a database. And they use the same camera at the same location to take these videos. So perfect for our training purpose. So we just use a database to train. So let me show you a demonstration. So what we do is we use a video input to the AI, then use that to predict the heat release rate and compare that with the oxygen calorimetry result. And once you train with thousands of these cases, actually the AI can pick up the heat release rate pretty accurate. Sometimes it may be underestimated because this is a two-dimensional image, so it cannot capture the depth of the field. So if you have very thick depths of the field, it will underestimate it. So, well, next step, if you use three cameras in different angles, may be able to solve that problem. So this is the idea. So once we train, we just randomly pick up some videos from internet, okay, and we use the algorithm trying to predict the heat release rate. Okay, so we tried with a car fire, we tried with the Christmas trees, and using this algorithm to trying to quantify the heat release rate. So we can do that for any kind of videos, but there are some tricks here. You have to zoom the fire, zoom the image to the right distance, to the same distance as your training database, because essentially AI is picking up the size of the fire. So what we are doing right now is we are developing an app so everyone can download it. The case is trying to help the fire service department because if there is a fire, people walking by, they will take out their phones to record these news, and we are say, okay, you can upload it to the fire service department, and they can, if it's real time, they can just pick up and know what's going on. And if it's for fire investigation, that can also be evidence for later legal things involved. So this is something we are developing. And ideally, we can put the same algorithm into UAVs. When there is a fire, the UAV just go there, start to taking videos and monitoring the fire evolution. That may be helpful for the later firefighting. So this is the second part. And the third part I like to talk about is digital twin. So digital twin, what's digital twin? So digital twin is something like come up 30 years ago, first proposed, I think, by NASA. and also these aircraft engine companies. So they have a physical, let's say, aircraft engine, and they have a digital engine in their computer. So in fact, if some of these airplanes have some accident dropped, it's not the airline knows that first. It's the engine company knows first, because all the engine, they have digital twin in their headquarters. So they will see whether their engine is working properly or not. So that's the concept can be applied to the building. So building digital twin is also very hard concept. You have a real building and you have sensors to transfer all the information into the computer. You have a build digital twin in the computer. So the idea is whether we can have the fire digital twin for the building as well. Okay. Yeah, so this is the concept is having a digital twin in the computer so we can monitor the fire in real time. So this is a digital twin we built for the test pit in the fire service department, but there's still a lot of things to go on right now. It cannot pick up the flash of the backdraft properly. So it needs more training in the algorithm, but that's the starting point. So later on, we feel like, okay, maybe the compartment fire is too complicated. Let's start with something relatively simple. Is we do the tunnel, because ideally the fire can only go left and right in one-dimensional way in the tunnel. So in order to build a digital twin, so we also need a lot of tunnel fire data to train the AI algorithm so it can show the fire profile in the tunnel. So I'm not a tunnel expert, so the first thing I do is to dig the literature to see if there are enough data in the literature. And it turns out, no data about tunnel fire. I'm not saying the researchers are not doing the right thing. It's simply because it's difficult to analyze transient data. So if you have space variation, you have time variation, it's almost impossible to analyze it. So what the researcher usually do is they only focusing on the steady state. So all the correlations you found in the tunnel fire is for steady state fire. They have the data. They did an experiment, they have the fire evolution, but they don't analyze that data because it's very difficult to analyze. And they don't report it. So in that case, there is simply no data we can use, even after reading like hundreds of papers. So that's a reality. We don't have these data. So the alternative way is we try with numerical data with the tunnel. So we run like more than 1,000 different cases for a typical tunnel. This is a tunnel in the Sichuan Fire Research Institute. They have a 140 meters long tunnel. So we did a massive simulation on that tunnel. And so this is a demonstration in the small scale. So I'll show you. So this is a small tunnel in our lab, only 2 meters long. So we have the sensors on the top of the tunnel, and it will transfer data to the cloud, and the data will passing through the AI, and AI will pick up the right image, the most close image of that tunnel. So let me show you a demonstration. So this is a tunnel. So on the top is the real fire. So that's a physical tunnel fire. And on the bottom, we have the digital twin. So for example, if we just move the fire, and you will see the temperature profile will change, and that pass through the AI algorithm. So it will tell, okay, it probably the fire has moved. So it will tell the digital twin to show this is temperature profile. In that case. Let's see. I think we have further moved that as well. Okay, well that's all. So only moved once. So this is if you move the fire, so the digital twin will sense it. Of course, there is certain time delays, but overall, it can capture the temperature distribution inside the tunnel. So potentially we can use that to the larger scale, real scale tunnel as well. So this is 2 dimensional. This is 1 dimensional digital twin. And currently we are building the digital twin for the tunnel testing facility we are talking about in Sichuan. So the idea is we have a digital twin in Hong Kong. So although we don't know what kind of tests they are doing, so if they do the test, actually our digital twin can show up what kind of fire they're burning. So that's the idea of remote monitoring. So that's still under development, and we want to build a three-dimensional interface in the Unity to show that. So this is one-dimensional. So we also tried the two-dimensional digital twin. So because tunnel is either left and right, but in reality, if you have large open space, so the fire could be moving around. So this is an idea we propose. So we have these smoke detectors. Some we have heat detectors on the top of the roof, on the ceiling. According to the regulation, you have to assign these detectors a certain distance away. So if you have larger space, technically you have a group of sensors, a matrix of sensors. So with this data, we can also pick up the fire location. Let me give you a demonstration of the two-dimensional digital twin we have. So this is our fire lab. So you can see the fire is here. And we have a digital twin here showing the location of the fire. And my student is now moving the plane. And let's see, so the digital twin is also showing the motion with some time lapse, like few seconds. And now they initiate a second fire. And the digital twin actually pick up the growth of the fire. So this is a kind of like demonstration. So in reality, most cases, we don't have CCTV camera inside of the building for privacy issues. You may have in the hallways. So if we have regular fire sensors inside like open plan office, we can capture the fire location and the fire size with this digital twin system. Okay, the first part I'd like to talk about is fire forecast using AI. And maybe that can help with the firefighting, but it's more challenging. So this is the major concept of our Surefire system. So it's part of the scope of the FireGrid project before. Instead, what we want is to have the sensors to measure the fire and put that into the cloud. And the data will pass the control center and learn by AIs, and the AI can predict what the fire will become in the next 5-10 minutes. And that information may be able to pass to the fire commanders, give additional information to the firefighters to deal with fire better. So that's the concept here. So we need the data, we need a sensor, we need a cloud computing, as well as a communication system to the firefighters. So the first thing we want to do is still the relatively simple case, tunnel, because tunnel you have relatively one-dimensional scenarios. So we want to see if we can predict the fire evolution of that tunnel, and we don't have enough data, experiment data, to training the database, to training the AI. So we simply use the numerical simulation build with thousands of these simulations and trying to predict the temperature profile of that tunnel. So what we have is to extracting the temperature profile and correlate with the temperature data measured by the sensors. So because the measurement is discrete sensor data, and for the output is what we want is two-dimensional temperature profile. So the training is covering these. So let me give you a demonstration. So the top one is the CFD simulation, and the bottom one is actually the AI prediction with 60 seconds lead time. So at least from the numerical point of view, it's reasonable, the prediction. And of course, it may not be able to capture plume structures. But in terms of fire hazard, it's not that relevant. We care about the global temperature profile. So that's the first step. We also tried that with what if fire is moving, can the AI predicting it also when the fire is actually changing. So the top one is the CFD simulation. The bottom one is AI prediction with 30 seconds lead time. And there's a heat release rate is changing. The fire location is also moving. So as you can see that AI actually can predict the motion of that the fire after you're training with enough database. Okay, of course, this is still in the numerical level. We haven't got experiment to demonstrate. And the second thing we try is whether we can predict the flashover or not. So what we do is use a small scale component. I think most of the fire lab has, and use a temperature sensor on the top of the ceiling. And we do like dozens of these experiments, some flashover, some didn't get flashover. And trying to use the temperature evolution data to correlate the probability of flashover. So I'll give you another example. So this is a demonstration we have. So the video is accelerated. The top one is the temperature data. The bottom one is probability of flashover. And we use temperature data to quantify, to correlate as the input. So right now, the probability of flashover is predicted to be 0 because it's still pretty weak. And now the AI is start to predicting, okay, in 30 seconds, it will start to flash over. And so this is a real flashover probability. So we use the spilled flame to quantify the probability of flashover. So this is a prototype demonstration for the small scale flashover predictions. And currently we are collaborating with the Hong Kong Fire Service Department. They have the demonstration for the backdraft container. So we hope whether we can predict the backdraft and the flashover in the real scale. That will be our next work. Okay. And the last part I briefly talk about the challenges and perspective in this area, something I think maybe was to discuss. The first is, can we trust the AI? So this is something people always question because AI is essentially a black box. So we don't know how it actually worked. So one of the example the AI community met is this case, whether you can distinguish husky from wolf. So most of the case, AI did a very well job, but this one. So this one actually recognized it wrong. It's the AI predicted it to be wolf, but it actually is a husky. So later on, the AI experts realized because during the training, the AI is not focusing on the animal, it's focusing on the background, focusing on the snow. So during the training, they realized the AI pick up, if you have snow on the background, it's a wolf. If you don't have snow, it's husky. So that's kind of like a mistake come from. So later on, they generated the attention-based AI. So your attention has to be focusing on the animal, the real things. So similar concept can be used in our case as well. For example, if we want to recognize a fire, we need to make sure the attention of that AI is on the fire, not on the background. So, but that's something I would say quite nature. For human beings, sometimes you get a bias. Like typically, if you see like black people, if you see Muslims, you have certain bias. That will happen in AI as well. So So the way to solve it is you have to generate a lot of data. The more you train, the bias you can avoid. And also you need to know the limitation of your tools. You cannot think it's perfect. And knowing fire dynamics is a best way for you to avoid the misjudgment by the AI. Okay. And for example, the Face ID cannot distinguish the twins, so the technology is not there yet. And I cannot distinguish twins either sometimes if they really look similar. So in another way, we should not ask too much about AI because even human beings cannot do this. Okay. And in fact, about this, I recently have more thinking about that. So we have a perception is like AI is not as good as human beings, but that's not necessarily true. So why can we assume humans' understanding is better than the computer? If the AI is trained with so much data, the data amount is way more than human brain, maybe they give a better result than the human beings. In fact, humans' understanding of the world is also misleading in a certain way. For example, if we think about the relative gravity, so we all believe Newton's law, the law of gravity, but Einstein say, no, there's no gravity. There's only a bending of space, time and space. So it's just about how do you interpret the world. So AI probably interpret it in a different way, and we interpret it in another way. As long as it works, I think we can trust it. The other question, and I think how to hide it. The other question is about sensor. I talked to the people in the industry. They all ask, do you want additional sensor? That additional sensor is something they don't want. They don't want to change the regulation and existing things. And my answer is actually no. I think we are pretty good. We already have so many sensors in the buildings. Sprinklers is temperature sensor, smoke detectors, heat detectors. They already collect a lot of data. We also have the air conditioning temperature panel. That's actually a thermocouple inside. So that's also a temperature sensor. And we also have CCTV camera everywhere. But we are not using these data. So most of the data go to the fire control panels and they don't even store it. And we have a Honeywell system in our lab. The heat detector, the data they collect will stop at 65 degrees because they thought the temperature data above 65 degrees is irrelevant. So they don't use that data, although they have the data. So the short answer, yes, we don't need additional sensor, but we need to use the data in a better way. So, and for example, the firefighter, the CCTV camera definitely can be used to track the people during the evacuation, but we're not using it. Of course, we can develop additional sensors. We have proposed some like spider sensors. If it reaches a certain temperature, we'll drop some thermocouples. And maybe some soft sensors can be put in the firefighters' clothes, give additional information about the fire environment. Or maybe micro GPS, these kind of small card can be put in the first aid kit in case someone, need to evacuate, but they get hurt, they can track the location and the firefighters can give priority to rescue these people. So sensors, yes, there's a lot can be done. And digital twin. So people have talked about digital twin 20 years ago, 30 years ago. So my department is building environment energy engineering. So I have many colleagues doing the environment, building environment and energy. So I talked to them, is the digital twin already something very common in your area? They would say, not really. So they have all the sensors, they have all the data, but just the technology is not there. So for example, this building, all the temperature are monitored to a certain degree, and you have the data in the cloud. But the current technology is only showing the temperature in the computer, rather than showing like three-dimensional mapping of the temperature. So it's more like a data logger rather than digital twin. They're just showing some temperature data. That's not the digital twin we need. We actually need a like three-dimensional mapping of temperature profile, fire hazard, smoke motion. That's the digital twin we're talking about. And the technology is not there. I think one of the major reasons is many people, when they talk about the digital twin, they talk about BIM, the building information system, building information modeling. But the BIM, it's a design tool. So it's used to draw like nice 3D models. It's not designed for data communication. What's good for data communication is actually the game engine. So most of the computer game engine, they actually have very powerful data communication. And we actually need to use that kind of tool to do the digital twin for the building. And we have a big gap here because most of the building model is in the BIMs. And the game engine is not for the building. So somehow we have to make the gap smaller into different communities. Some other things we are thinking about is, can we do smart evacuation? So if we know the, okay, this is actually a demonstration my student did. So if we know the fire and the hazard level inside the building, we can actually guide people to evacuate into the shortest and the safest path. And that can be done if you have these smart system coupled with these dynamic access signage. So, but this is still very early stage because I imagine there will be legal problems. So what if you guide people into the fire? So who's responsibility for that? And that will come when we have a smart system. So we need to build that smart system first, then we can have some signage, maybe UAVs to guide people out as well. And UAV and robotics, I think, will be used more and more. For example, in the wildland fire community, some of them, they already have like a watchtower coupled with UAVs. When there is like a wildland fire, a bushfire, so the UAV will just fly and go check around. So we should do that for the building fires as well, the urban fire as well. Maybe there are some UAV stations, and before the fireman can run out, they probably can just go check around. And that could save a lot of time. The other thing is about robotics. I think that's also the future here. Actually, for example, in Hong Kong, we already bought a lot of firefighting robotics for the fire service departments. They actually use it. But if you look at these robotics, it has nothing special compared to the toy I played with it when I was 10. So it's just remote control car. So not intelligent. These robots would not facing the fire and to shoot it automatically. They need a human to control it. So yeah, they are robots, they are not really smart. So there's still a lot of things can be done in this area. Okay, and software and apps. Okay, so this is actually an app we developed for the Surefire system. Okay, it's not public yet. You can only access from our university. And maybe it's out. Try it again. Yeah, okay, you can actually access it. Okay, so ideally we want to build this smart system and maybe customized for different applications. If you have specific building, we want to design a customized smart firefighting system for you. So this is our next step. So, but still a long way to go. Okay, let me give a very short summary. I think AI is a very useful tool for the fire engineering and the researchers, but it's just a tool, nothing fancy. You don't have to be an AI expert to use it. You just need to know how to use it and know its limit. And knowing the fire dynamic is still a good guarantee for you to use it properly, just like using CFD. And I think AI is very good to do the identification, just like Face ID we use. And fire data train will be an important component for the smart building management. And we need an IoT sensor network. And we already have a lot of sensors, but we just need to use the data in a smarter way. And that's not something easy we can convince the hardware companies. And UAV robotics will be the future. So with that, I finished my talk. So I'd like to thank the team and also the sponsors from the Hong Kong government and the collaborators all around the world. Thank you. Any question?
So thank you for the presentation, Xinyan. We have a couple of questions from online, so we could start by those, and then we can transition into something more hybrid. Yeah, thank you for a really comprehensive presentation. Really interesting data there. The first of the questions is related to one of the things you were talking about, so the density of sensors. One of the attendees would ask if the traditional code spacing, I think he refers here in Australia, it's 7 by 7 meters for thermal devices to get so he wonders if that density would be enough to give data for the predictive digital twin model, or if you would need a higher density or a better sensitivity of the sensor.
Yeah, I think that's a very good question. So I don't know the code here. Actually, in Hong Kong, it's 2.8 meter, the distance. So the sensor density is quite high in Hong Kong. But my conclusion is we don't want to change the code. We don't want to make the code more strict or not. What we want to do is we can design a system based on your current sensor density. If you are very dense, the prediction may be higher. If you only have even just one sensor in a room, I think it still can give some reasonable predictions up to a certain point. So it's better than nothing.
All right, thank you. The same colleague has a question regarding the trade-off between the costs of sensing more data, versus the available tools that we already have, such as thermal image cameras. So says it's visually faster and misdirection of the fire might be an disadvantage. So is it to use automated fire robots, drones to action the firefighting an advantage? He says if there is any advantage compared to thermal cameras and traditional firefighters.
Okay, so thermal camera is quite expensive. We all know that, and most of the building does not have these kind of things. So I would say regular CCTV camera are pretty good. Of course, they will be blocked by the smoke, but before they are blocked, they can capture the fire, smoke, and human beings very well. In terms of the IR camera, I think some firefighters in liquid, that's good, but it's probably not necessary because once it's covered by the smoke, who knows what the infrared camera is really reading. In terms of robotics and UAVs, that's a good point. So I talked to the expert about doing the UAVs. They talk about all the challenges of how to maintain the UAV in the fire and something like that. So I told them, you miss a point. Who care about if your UAV is coming back or not? So as long as it can save people, I'm happy to lose 10 UAVs. So the principle is different. We want to get more information with a low cost. Do you want to lose 10 UAVs or lose one firefighter? So understanding that, the principle will be much easier. So if the UAV lasts 5 minutes, probably it's worth it already.
All right. And last, we have another question related to if it's possible to connect AI fire to mobile phones automatically through Wi-Fi for persons in multiple occupancies to evacuate?
Yes, very good question. So, yes, so ideally, you can try that system. Even you don't do that. Oh, people may question whether AI gives the right result. But in fact, in most of the evacuation process, people just follow other people. So you don't know whether you are following the right path or not. So if you have alternative information, that's good. And the AI should always be in the cloud rather than doing the calculation in your own phone. So your phone should only be a display device rather than doing the because sometimes these calculation actually take a longer time. So should be in cloud supercomputing.
And on that note, could it be a good strategy to just use the cell phone of the fire warden or whatever is in in charge of the evacuation of that level?
So
Or
if
would-
you are in the forest fire, I think maybe the phone is okay. But if you in a confined space, pinpoint your actual location in the three-dimensional building environment would be quite challenging. If it's in the bushfire, maybe okay. So the approach I think is we should use more informative access signage. So give sound or arrow cross to guide people. That may be more reasonable. In fact, during the evacuation process, it's not always more information is better. Sometimes simple, concise information is better than more information.
Thank you. So are there any questions from the room?
Yes. In the tool, the online tool that you presented, right back at the start, I can't remember what it was called, IFE something.
Oh, yeah, I have.
Here. You said that this has been trained with 1,000 CFD simulations. You've given bounds for the inputs there. So the width between 30 and 90 meters, the height between 10 and 20 meters.
Yes.
The fire size between 0.5 and 10 meters. I assume that those limits represent the limits of the parameters or that you run the training based on. So I guess I kind of have two questions. One of them may be a little bit flippant, so I'll start with the other one first. What happens if you, maybe you put a error check and you see you can't do it, but what happens if you go outside of the bounds that are given here?
We make it an arrow, so it won't run. But ideally, you can.
What happens if the error? What happens if you hadn't coded that as an error? What would the AI do?
So AI will give some prediction. He think makes sense. So it will be deviate a lot from CFD. If you go out of the bound.
Okay.
Fundamentally, what we think is AI is just multi-dimensional fitting, multi-dimensional nonlinear fitting of different parameters.
And so my slightly flippant question, what's the benefit of the AI as opposed to just having that database of 1,000 training cases?
I think it will be a very good start for the engineers. They always trying to look for the limiting design case. Instead of running very expensive CFDs, they can just use this tool to get the rough design idea.
But you've already run those CFDs, so why not? Why do you need the AI? Why not just make the CFD? So what's the point of the AI tool in this case?
Because it's faster. It's just
And looking at the CFD result.
CFD you have to run for a long time.
But you've already run them. You've got 1,000.
But it's
cases that you've changed.
thousands is small enough. Considering the reality, you have different shapes, you have balconies.
So I
So
assume you would interpolate between the two closest cases.
so actually this tool is not designed for the designers. It's actually designed for the AHJ. Because sometimes these designers give random design and you have to run the source code to know whether it makes sense or not. This gives you a quick check.
Well, but that's assuming that the database that you used to train the AI made sense in the first place as well.
Yes. So we test that. the roof shape and the balconies, the slabs, they have some influence. But if we including more database into it, it will train better. Plus, the reality is you can all kinds of shape for the atrium, so it will be more complicated than this simple geometry. So it's a reference. It's a good reference.
Thanks for the presentation, Xinyan. Lot of interesting and very upcoming work. I guess I have a question with respect to digital twins. So I'm not an expert in the space by any means, but I'm a bit aware of how digital twins are formed in oil and gas and in aerospace, and they're not mature there, but effectively you're pretty much spot on in terms of what they achieve, but they add another layer of functionality, which I think actually makes them a digital twin rather than sort of just a pseudo representation of what's happening concurrently in the model or in reality, which is they have some element of forecasting embedded in them, right? So they can take real-time data and then using some sort of, forward model of some description, they could effectively predict structural health locally or my mechanical integrity in one of my blades, or potentially, whether or not I'm at risk of this vessel forward in time undergoing an overpressure event and so on. So in the case of your digital twin for fire, I mean, what is your mechanism by which you're going to develop your forward model? I mean, what kind of models do you need to use that sort of work in the context of fire? Because they have to be quick, no?
Yes, in fact, once you train the model, you get forecast automatically. Because when they train the model, they train like 1 minute or 5 minute span. They use 1 minute of data training. So you can get the current moment. You can also get the prediction in like 1 minute or 5 minutes.
So are you constraining it though, or are you trying? So there's also the concept of like data assimilation, right? Where you take an existing model with some sort of physical bound, right? It's semi-empirical model or whatnot, or an analytical model. But at least, you essentially use your data, your forward model, maybe even a CFD to try and target it in the right direction so that whatever forward model when you combine it with your AI, it at least points you roughly in the right direction and so on. Are you using is it just purely based on AI, or are you planning on implementing some sort of forward model that's based on physics?
Okay, so because when we train it, we train like a whole time history.
Right.
So they know that case train the whole history. So automatically, when you predict it, it predicts the whole history. Of course, when you input the new data, the future will change. So, but that prediction is not based on physics. Actually, it's just AI, intuition.
Okay.
AI is intuition.
Yeah. But you would agree though that the forward model part is critical for a digital twin to give utility, or in the definition of it?
Not really.
No?
In fact, I think the forecast is for the firefighters. I think if you know the current status, it's pretty good in many applications.
Right.
It's hard. For example, if you see the smoke outside the building, if you can identify the fire inside, it's already quite good. Predicting it will be questionable.
But you can, you don't have to predict it to its end state, right? It's live data. So, your firefighters in theory could get live forecasting of, should I enter this room or not? And, how long can I stay in this room? I mean, forward forecasting gives you really valuable time or really valuable data in terms of forming your risk parameters for operating in the space, no?
Yeah, I fully agree. And if you have more historical data, that will help.
Right.
That's the reason if some UAV can fly there, start to look at the fire from the beginning, that will be really helpful.
Right. All right. That's really interesting.
I have a question. So the topic is very interesting, and thanks for the presentation. It's very impressive. I have a question asked for the AI fire cognition. So I understand that the release rate prediction algorithm was trained within the NIST database. And I totally agree with that. The database is a good starting point, and everything will rely on that. But within the same database, the image or say the video with more or less the same resolution, brightness, exposure, and the angles as well. But so if you pick up another image or video from the same system, from the same database, it should be reliable to give you a good prediction. But if you pick up like you did for a random burning car, how can you convince that the prediction is really good?
Okay, very good question. So when we say we train the NIST database, it's actually dividing the database into 60% for the training, 20% for the validation, and the other 20% is purely testing. So that testing is already like prediction. They are not involved in the training process. Otherwise, it's it's a loop. So basically, the AI model is already be able to predicting the test case very well. And what you mentioned about the angle, yes, we are working on that, and also the brightness and the color. The result is actually surprising. We haven't published it. It's actually we found that the color and the brightness of the fire is noise. It's actually noise. So what AI's attention is actually the size, because if you have cameras with different background, if you took the same fire in the daytime, in the nighttime, you have very different brightness, very different color. So in fact, AI recognizes that should be noise, only focusing on the size of the fire.
So you mean there are experimental work going on?
Yes, we also
The verification.
now what we do is we convert this color video into gray video, then convert it into binary videos and train them, see which one is better. Actually, binary video is better than color video.
Okay, so I was wondering, has sort of broken down any of the burden test with measured periods, right?
Yeah.
Compare with the prediction, how good the prediction is.
As I mentioned, is that 20% of testing is already directly compared with the NIST database. So that 20% of test is not in the training. It's purely verify your prediction. We also do with the scale in our lab. We put a pool file measuring the mass loss rate. That also very accurate.
Okay. Yeah, that's my question. Thank you.
Thanks.
I guess one final one. So you've talked a lot about AI and deep learning and so on. I was just wondering, how sensitive are some of the results to, so I assume that when using this, a certain algorithm, depending on the application, have you ever tested the sensitivity of one algorithm versus several others? I mean, is it very sensitive? So say if I or someone else wanted to try and replicate, the sort of the same results using the same database, would we be able to, based, algorithmically?
Yes, in general, it's quite sensitive to the data. So what we do is we usually reduce the frequency of sensors. So let's say one data every second or one data every 2 seconds. Because if you have like 10 hertz of the sensor, so the prediction will be like crazy vibrating. So it's not really helpful.
All right. There is another question online. So we could go with that one. So one of the attendees is wondering if in the future, as a perspective, there is any chance the bounds for the compartment for the first tool that you presented, if the width of the room could be updated to less than 30 meters. The reason she wonders that is, like it's not applicable to compartments or the really open, large.
Yes, definitely. As long as our database, including these small compartment or region, that can predict as well.
Right. All right.
Thanks.
Well, I'd like to thank you again for the presentation and for these planning. So yeah, if you want to pass on your contact details in case someone wants to.
So if anyone is interested, just email me, shoot me an email.
All right. Thank you for your kind presentation, and also we would like to remind our attendees that we are going to upload a version of this presentation online. Yeah, a recording of this one. So please follow us on YouTube, Eventbrite, and all our social media platforms. So thank you very much. See you next time.